So last PowerPoint, what did we talk about? Last PowerPoint, we talked essentially about parameters and statistics. We said that we're often, as researchers or statisticians, interested in characteristics or properties of a population. But because of the limitations of the world we live in, we cannot look at the entirety of the population. We're forced to look at a portion of it. We're forced to look at a sample. More specifically, as an example, we're often interested in the mean of a population. We cannot observe that, so instead we take a sample, we look at the mean of the sample. That's a statistic. It's used as a best guess of our parameter. The parameter is the mean of the population. We said that the sample mean is a best guess, our best guess for the true but generally unknown population mean. So we're left with the question, how good of a best guess is it? Now, to be able to answer that question, we need to make a few observations. The first observation we made at the end of the last PowerPoint, and that is that all statistics, specifically the sample mean, are random variables. And as such, they're governed by all the rules of random variables that we have spent the majority of Chapter 4 talking about. In particular, they have a probability distribution, they have a mean, and they have a standard deviation. So, the sample mean x bar is a random variable, and we are going to spend this PowerPoint talking about its various properties. So, of the random variable that is the sample mean, let's explore it and let's describe it. The sort of mathematical theorem that lays out its description is called the central limit theorem, so that's what we're going to talk about in this particular PowerPoint. Let's start with an example. Let's consider an admittedly absurdly small population. So this is our population of 4 students, Amy, Bob, Cindy, and Dan. Now I promise you, the mathematics are still the same if we did a population of 400,000 students. It would just take a lot longer to go through this example. So, let's keep it simple. We have our population. Let's say that the height, x, of a randomly selected student is a random variable. It would be. If we picked a student at random and recorded their height, then that height would be a random variable. Alright, so if x is their height, what is the probability distribution of x? There's only 4 people in our sample. X actually only takes 4 values. We would often think of height as being continuous, but in this limited example of only 4 people, where it's only taking 4 values, it actually becomes a discrete sort of random variable or discrete situation. So, if I pick them randomly, and they all have the same chance of being selected, that means that they all have a 1 in 4 chance of being selected. There are their heights. Amy is 64 inches, Bob is 71 inches, Cindy is 58 inches, Dan is 84 inches. Wow, Dan is quite tall. I think that's 7 feet tall, actually. Now, let's discuss the properties of x. In particular, what is the true mean height of x? So at this point, we're actually calculating the population mean, the average height of our population. Now, right, if we really wanted to do this for all Westchester students, it would be the same process. It's just we would have to get 400,000 heights instead of 4. We would still sort of add all of them up and divide by essentially 400,000. So remember, the mean of a random variable is the outcome weighted by its probability. In this case, they all have the same probability. So it's 64 times a fourth, plus 71 times a fourth, plus 58 times a fourth, plus 84 times a fourth, right? This formula is coming from our very first Chapter 4 PowerPoint. If you don't remember it, then review it. If I crunch those numbers, I get 69.25. The average height of all students in my population is 69.25 inches. Now, let's try to simulate reality. Let's say that we do not have the ability or resources to look at the entirety of our population. I know, it's silly in this example, but I promise you this stuff generalizes to a larger sample and a larger population. Let's say that we can only look at a portion of our population. We can only look at half of it. We can look at 2 students. So we take a random sample, a simple random sample, as discussed in Chapter 1. We take a simple random sample of 2 students, and we compute the sample mean. Note the sample mean, x bar, is a random variable. Let's see that more clearly on the next slide. Now you may or may not remember from Chapter 1 that a simple random sample essentially means that every sample has the same probability of occurring. In this situation, there are actually 6 possible samples that could occur. We could select, I have all the samples listed on the left. We could select Amy and Bob, Amy and Cindy, Amy and Dan. Those are all the Amy samples. We could select Bob and Cindy, Bob and Dan. Those are all the Bob samples. Or we could select Cindy and Dan. Those are the remaining Cindy samples. And for each sample, we could compute, right, the average height. So if my sample consisted of Amy and Bob, then the average height would be 64 plus 71 divided by 2, right? That's the sample mean. Add them all up and divide by the size of your sample. So here our sample size is just 2. I would get 67.5. I do that for the remaining 5 samples. Now I apologize. It looks like I missed a 1/6 there, but there should be an extra 1/6 for the Cindy Dan sample. So I have 6 possible samples. All of them have a 1 in 6 chance of occurring. So notice, the average height takes different values with different probabilities. That's what I said in the previous PowerPoint. I'm making it explicit here, right? The average height takes a value 67.5 with a 1 in 6 probability. Takes the value 61 with a 1 in 6 probability. Takes the value 64 with a 1 in 6 probability. Okay? Now, what is the mean of x bar? Again, it sounds a little weird to say what's the mean of the mean. But remember, x bar, the sample mean, is just a random variable. So I'm asking, what's the mean of this random variable? Well, again, I take every outcome, I weight it by its probability, and I add those numbers up. So in this case, they all have the same probability. So I just take the outcomes, multiply them all by 1/6, add them together. I leave it to you to verify that if we do that, we get 69.25. 69.25. 69.25. Where have I seen that before? Where have I seen that? Of course! Wow! 69.25. That was the mean of x, wasn't it? That was the average height of all students. Holy smokes! What a great magic trick. Do you think it was a coincidence that it ended up being the same? Well, I'll tell you right now, it's no coincidence. But before we explore that idea a little bit further, I want to talk a little bit about what we're talking about here. The true mean height of our population of students, right? The true mean height we saw on the previous slide was 69.25. Now, if we take a sample, we get different sample means. Remember, we said in practice, the sample means are our best guess for the population mean that we usually don't know. So notice, right, if I took my first sample, which was Amy and Bob, that's the 67.5. In that case, the average height of my sample is 67.5. Based on that sample, I would guess that the true mean height for all students in the population is 67.5. Am I correct? No, I'm off. I'm actually underestimating it. But am I close? Yeah, I'm reasonably close. I'm within about 2 inches of the correct answer. Notice if I take a sample of Amy and Cindy, who are my 2 shortest students, I get an average height of 61. I very much underestimate the average height. Right? And I could go through the rest of the samples. If I take a sample, what is that? I think that 77.5 would be maybe Bob and Cindy. I wonder if I did some bad math somewhere. That seems a little bit high to me. But one of those samples gives me a 77.5. Probably I would think that has to have Dan in it somewhere. Maybe that's Bob. Yeah, it's Bob and Dan is who that is. Bob and Dan are our two tallest people. So all right, I think this is okay. So if I take a sample of Bob and Dan, my two largest people, I get a sample mean of 77.5. Right? In that case, I have a quote flukish sample. I would overestimate the true mean. I would say it's 77.5 when in reality it's 69.25. So again, the sample mean is a random variable. Sometimes, as we can see, it underestimates the true mean. Sometimes it overestimates the true mean. But the fact that the mean of the sample mean is exactly the true mean, the fact that its mean is 69.25 essentially says that on average it gets it right. On average, the sample mean is the true mean. On average, we get the true mean right. So, wow, this is going back to the fact that those two numbers were the same, and as I mentioned, the equality of means, the fact that the mean of the sample mean was the same as the mean of x, is no coincidence. If you want, go ahead and try. Any numbers you plug in for those heights, if you go through that exercise, you will always get that the average height is equal to the average of the sample mean. This astounding fact is just one component, if you can believe it, is just one component of an astounding statistical fact known as the central limit theorem. The central limit theorem is the most important, most magical, most miraculous theorem in all of statistics, perhaps in all of life. What is the central limit theorem backwards? Well, it's commonly abbreviated CLT. CLT backwards is what? It's TLC. And what does TLC stand for? TLC stands for tender, loving care. How do we treat, how do we handle things that are precious, that are important? We treat them with tender, loving care. It is no coincidence that the central limit theorem backwards is TLC. And so here it is, in all its majestic beauty, the most important theorem in all of statistics. Consider a random sample of n observations selected from a population. Any population. That any population is the true miracle of the central limit theorem. With a mean mu, some arbitrary mean, and a standard deviation sigma. So a random sample of n observations from any random phenomenon with any mean and any standard deviation. Then, it's true that if your sample size is sufficiently large, the sampling distribution of x bar, just the probability distribution of x bar, is going to be really close to a normal distribution. Something that we know how to deal with and we've spent a lot of time practicing. Well, every normal distribution has a mean and a standard deviation. So what does its mean? Well, the mean of x bar is the original mean. That fact right there we already observed. We observed that fact. Another fact is that the standard deviation of x bar is the original standard deviation divided by the square root of n. You need to memorize both of those facts for your upcoming test and for your comprehensive final. I keep referring comprehensive final. That's, of course, for fall and spring semester. I don't generally do those for the winter or summer sessions. It turns out that the larger the sample size, the better that normal approximation is. That is, the closer the probability distribution of x bar is to a normal distribution. Wow. I don't know. I feel like it's not a teacher's place to sort of lecture on God or to lecture on religion or to lecture on things like that because, right, I maybe am in some sense a position of authority and I don't want to abuse that. So I avoid talking about those things generally. But I do have to say, there are certain things that I won't say it makes you believe in say, God, but maybe makes you believe in some sort of higher power, that maybe there's something sort of above and beyond us, that there is something out there that creates such magic, such a miracle, right? Like, I mean, we've all had these moments, right, where you wake up and you go out in the morning and you see this beautiful sunrise and you're sort of struck by the immensity of life, right? And you just think, wow, there's something bigger and larger and just magical out there. Right? The birth of a baby, such a miraculous thing. Life creating life. Well, the central limit theorem is like a baby being born during a sunset. That's how incredible it is. Do you remember way back in Chapter 2? In Chapter 2, we were debating the pros and cons of means versus medians, and I said that there's a miraculous fact, there's a specific reason, there's something that makes the mean so incredible that we want to use it whenever possible. That magic fact is right here before us. It's that central limit theorem. It's that laughing, happy, freshly born baby in the midst of a sunrise in the Bahamas. That is why we use the mean as often as we possibly can, because there actually is a central limit theorem result for medians, but it's not nearly as powerful, it's not nearly as strong, and so it's not nearly as widely used. Now, I said in the previous slide that the sample mean follows a normal distribution if the sample size is sufficiently large. The question becomes, what is sufficiently large? Well, there's basically two ways that the sample mean can follow a normal distribution. And we only need one of these two to happen. If the underlying distribution x is already normal, right? So we're talking about, like, if that underlying distribution x, maybe x is the weight of a single walrus. If we know that that follows a normal distribution, then it turns out the sample mean is normal for any sample size. However, if we know that x is not normal, or, as is more often in real life, if we simply don't know what its distribution is, then a commonly used rule of thumb is that if your sample size is 30 or more, then that's sort of large enough that the sample mean's distribution is close enough to normal that we can essentially treat it as if it really is normal, right? For instance, using things like normal CDF to calculate normal probabilities. So what? Who cares? What's the big deal about the central limit theorem? The central limit theorem is so important because the fact that we know that the sample mean follows a normal distribution and that we can know what its mean and standard deviation is means that we can use all of the techniques, all of the tricks, all of our practice for dealing with normal distributions that we've spent this chapter sort of sharpening and honing. We can use all of these to answer probability questions about sample means. Now you might say, who cares about answering probability questions about sample means? But I'll show in the next PowerPoint that being able to answer these questions is of critical importance if we want to answer that question, how good of a best guess is the sample mean to the true mean, right? Which is the question that we've been asking ourselves, right, for this PowerPoint and the previous one. I actually thought I had deleted this slide. I decided I didn't really want to talk through it, so let's actually pretend this slide is not here. Close your eyes. This slide never happened. Close your eyes again. This slide never happened. Close your eyes one more time. This never happened. And this never happened. It is an interesting example, but I think it detracts. My experience has been, as I've sort of given a test run through a number of classes in person, that it maybe detracts from the big picture. What I might do is take this example and just make it its own little side example down the road, but for now let's not worry about it. Let's instead focus on this observation. The central limit theorem, remember, the central limit theorem says a few things. One of the things it says is that the mean of x bar is the mean of x. Again, we already saw this when we did our example at the beginning of this PowerPoint. When we saw the mean of x was 69.2, and then we did the mean of the sample mean, and that was also 69.2. 69.25, sorry. That essentially tells us, like I said, sometimes the sample mean overestimates the true mean, Sometimes the sample mean underestimates the true mean. On average, it gets it right. That fact that on average it gets it right means that it's unbiased. It does not have a bias. Unbiased means that the sample mean does not consistently over or underestimate the population mean. Another observation is that the variability in the sample mean shrinks as the sample size increases. Right? The variability of x bar is the original variability. It's that standard deviation sigma over the square root of n. So, as my sample size gets larger, I'm putting a larger and larger number in that denominator. A large number in the denominator makes the overall number small. Agreed? 1,000,000 is a big number. 1 over 1,000,000 is a very small number. So as my sample size increases, the overall variability, the standard deviation of x bar decreases. I can combine these observations in the following way. So the sample mean is always sort of tethered or tied to the true mean, right? It's always centered around that true mean. And as my sample size gets larger, so you could imagine, I have the sample mean follows a normal distribution. So I have that nice bell-shaped curve. That's describing the probability distribution of the sample mean. It's centered at the true mean, right? And we know that as my sample size increases, the standard deviation of x bar decreases. So again, think about what that does to the shape of our normal distribution. A smaller and smaller and smaller standard deviation sort of makes that normal distribution skinnier and skinnier and skinnier. It pushes that probability, it pushes that area towards the mean. Now, that area is essentially outcomes of the sample mean. So what that's really doing is right, the variability, on average, the sample mean is the true mean. And as I take a larger sample, the variability decreases. So that means, on average, it's closer and closer and closer to the true mean. Combining these facts leads us to an answer, right, to the question, why is the sample mean a good guess for the true mean? We could answer that question by essentially saying that it's a good guess because the sample mean converges to the true mean. It zeroes in on the true mean as the sample size gets larger and larger and larger. That's part of the central limit theorem. This phenomenon, this sort of corollary of the central limit theorem, is known as the law of large numbers. There's still a lot more for us to do with the central limit theorem, some pretty useful things. We're going to further explore the question of how good of a guess the sample mean is for the true mean, but right, why don't we take a little bit of a breather before then.
Sorry about that. I guess I lied. We will we'll take a breather probably after this slide. So the last thing that I wanted to mention in closing is this idea of normality. The normality is probably the most important aspect of the central limit theorem. Right, central limit theorem had three pieces: the distribution of the sample mean, the mean of the sample mean, the standard deviation of the sample mean. Of those three, the distribution, the fact that that distribution under certain conditions is a normal distribution, is a normal random variable, that's the biggest deal. Why? It's the biggest deal because it allows us in practice to compute probabilities using all the techniques that we've talked about. In particular, it allows us to actually make good use of all that time we spent perfecting the calculation of normal distributions. It allows us to use normal distributions in a meaningful way, even in situations, and this is a big deal, even in situations where the underlying distribution is unknown to us. Wow. Now this is really sad. This is a sad idea. Thankfully, it's also an idea that's not true. But if there was no central limit theorem, oh dear, what a tragic world. If there was no central limit theorem, this class would be over right now. Oh, I know. I'm like you. I'm getting sad just thinking about it. That is, with no central limit theorem, there'd be no more to talk about. If there was no central limit theorem, you would take a test, you'd be done with this class. Oh, can you imagine? Thankfully, though, we live in a world where there is a central limit theorem. Thanks, central limit theorem. And we'll see that it's this central limit theorem that makes possible everything that's coming up for the remainder of this course. For the remainder of this course, we're getting very, very close to taking some of these abstract ideas and making them applied. We're taking some of these abstract ideas, we're making them tangible, we're making them cool. And all of this is made possible thanks to the sponsorship of the central limit theorem.